Thank you very much. So the presentation is about hierarchical demand forecasting benchmark for the distribution grid. So basically we provide a data set and also a benchmark in terms of different forecasters and how better they score compared to the other ones. So as all of you may know, distribution grids are, most of them, radial in nature, which means that they present a tree-like structure. And in this context, it is important that when you're going to forecast the power at the different nodes of the grid, all the forecasts for the hierarchy are consistent. And why so? Because nowadays, more and more DSOs are trying to provide services to the upper level of the grid by shifting flexibility or let's say the demand of some users at the lower part of the grid. And for doing this, it will be better if you have a consistent forecast which sum up consistently through the hierarchy. Otherwise, the optimization could be not as good, let's say. So compared to other existing data sets for benchmarking forecasters in this hierarchical setting, our dataset difference is in three key factors. The first of which is the scale. So in our dataset, the top node is a medium voltage, low voltage transformer, while in other existing benchmarks, the scale is a state level typically, so much bigger scale. We have a lower sampling time. We have 10 minutes sampling time versus typically 1 hour. So we are closer to the typically operation timings of system operators, and also to building timing, which is usually 50 minutes. And also we included weather forecasts from the MetaBlue numerical weather prediction service. And more in detail, here you can see the quantities that we provide in the dataset. We have the active reactive power, total harmonic distortion, the magnitude of the voltage for each of the phases. Then we have also the frequencies and the mean of the power. Those are provided with 10 minutes sampling time, while numerical weather prediction quantities like temperature and the solar irradiation and so on are provided by a sampling time of 1 hour and updates of 12 hours. And here you can see the link to download the dataset, which is on the top right of the screen for the rest of the presentation. So the measurements refers to the city of Role, which is located in the western part of Switzerland. And its dataset consists of secondary substations and low voltage cabinets. As you can see, the city is pretty small. The measurements were taken using Class A power quality meters, which were manufactured by Depsys, which is a Swiss-based company. And the different time series present a different level of forecastability. Here you can see on the top of the image time series which is more likely to be easily forecastable because it shows a very strong circadian pattern. While on the bottom of the image you can see a time series for which forecasting is much harder due to spikes and not so strong circadian patterns. Out of the 62 power meters that we have, we kept only 24 time series, which we select based on the number of nonce in the time series, basically. So that at the end we have a 24 time series, which spans almost 1 year of data. So to compare the different forecasters, we used a rolling window approach, in which every 10 minutes we shift the testing window of 24 hours by 10 minutes. So that at the end we had around 52,000 day-ahead tests. So a lot of tests. And we coupled this strategy with a 10-fold cross-validation. Each of the 10 folds were divided in segments of 10 days, out of which we used only the first 7 to train, and with a day of gap, we used the 9th day for testing. This was done to avoid too much overlap between training periods and test periods. So namely, we test the different models, which were the persistent model, bagged Armax model. So we had different Armax that we trained on different periods of the dataset and then bagged together. Then we had the trended alt winter, which ran on the trend signal using numerical weather prediction with double seasonalities. Then we have a K nearest neighbor and a light G boost model. And for each of these, we also retrieve probabilistic forecasts. For the first three models, we used an a priori technique. So we gathered the error on train set, divided it by beans, and indexed by the hour of the day and the day of the week. While for the last two, we used different techniques. For the KNN, we used just the distribution, the quantile distribution of the neighbors. While for the last one, light G boost model, we directly fit the quantile loss function for the quantiles. On the right, you can see some examples from the persistent Armax model, and those are the one related to the left models. It's important to stress that we did not perform hyperparameter tuning for the models, just we assumed reasonable parameters. And we did not perform feature engineering, and this was done to provide a vanilla benchmark for the forecasters to be compared with others. So we retrieved some deterministic and probabilistic scores for all the forecasters. On the left, you can see the mean absolute percentage error for the different forecasters, normalized with the performance of the persistent model. For example, on the left, we have the Armax model. You can see on the x-axis, we have the time at which the prediction refers to, while on the y-axis, we have the time at which the prediction was done. And the score is organized in these metrics, in which you see that the counter diagonal are basically hours of prediction around the midnight. And in this case, you see that around the midnight hours, the Armax model did not perform better than the persistent model. This was because these scores refer to the top layer of the hierarchy, so the aggregate time series, which showed a strong circadian pattern. On the other hand, you can see that, for example, the large boost model performs always better than the persistent model. On the right, we have instead a probabilistic score, which is the mean of the pinball loss function or quantile score. So this one, the lower the better, basically. And once again, you see that the rank of the forecasters is the same. So we have a large boost model which perform better with respect to the other one, and the persistent model which scores the worst. So we took all the 24 time series and we fictitiously aggregated them in order to have a hierarchical data set. So we have a 3-level hierarchy. We have a top one divided into sub time series and so on. Out of this hierarchical structure, we test all the forecasters on the top and on all the other time series. And on this table, you can see the scores referring to the top layer and the average of the scores with respect to the bottom time series. For example, you can see for the MAPE, we have for the large boost model a 3% MAPE for the top time series, while on average we have a 9.8 MAPE for the bottom time series. Of course, we wanted also to provide a benchmark for hierarchical forecasting techniques. So we combine two different hierarchical techniques with other two techniques to estimate the sparse covariance matrix, which is needed for these hierarchical techniques to work. Namely, we compare the MINT approach, which minimizes the trace of the covariance matrix of the revised forecast through generalized least square, with a Bayesian approach, which assumes that the joint probability of the errors is Gaussian. This last method especially can provide a consistent probability distribution through the hierarchy. And then we coupled with two other techniques for the covariance matrix estimation, namely the shrunk method and the graphical lasso. On the right, you can see the relative improvement in terms of root mean square error for the bottom time series divided by beans of 4 hours each. So in this case, you can see that the improvement for the bottom time series is not high. It's almost negligible because we are always under 1%. And sometimes the techniques actually worsen the result. The only exception is the couple of the technique mean T with the graphical lasso technique, which always improve also the bottom time series. Well, in this picture, you can see the same scores for the top time series. So in this case, we have a greater improvement. All the techniques can improve the forecast of the top 10 series. And we have an average improvement of in the order of 8% in relative change of root mean square error. So also in this case, we see that the couple winning is the mean T with the graphical lasso technique. At the end, we hope that this dataset can be useful to other researchers in order to test different hierarchical techniques in this particular setting. So thank you very much. And if you have any questions, I will be glad to answer, or you can also write to me.
Great. Thanks a lot, Lorenzo, for this. We already have one question from Mes. The question is, how did you integrate the solar PV forecasts or data into this?
Yeah.
Or how would you? Yeah.
Yeah. For some of the techniques, it wasn't possible. For example, the persistent model cannot. But for the others, we had different techniques to include this information. For example, for the RMAX, the exogenous part, where the meteorological condition, while for the trended alt winter, we use the radiance and the temperature at the point in time at which the prediction was done in order to detrend the signal, and then we run the alt winter lately. While for the KNN and Legge Boost model, it was natively supported, so we can easily plug them into the algorithms.
Okay. Thank you. And then also Rahul asks a question if you have analyzed the performance even for low time resolution, like sub-minute scale, and if you could comment on this.
No, we didn't, because we on purpose we choose to fix the time scale of the data set to 10 minutes because we thought that this was a meaningful resolution. Of course, we could have done bean aggregation to increase the time step, but no, we did not change the resolution of the data set.
Okay. Thank you, Lorenzo.